The title of this session is actually Ear and Behavioural Biometrics, but when you look at the papers we could actually retitle the session as Ears, Signature, Speaker and Keystroke, covering the 4 papers that we have. So our first paper this afternoon is on the robust localization of ears by feature-level fusion and context information, and is going to be presented by Annika Flug.
Thank you. So it's okay. Hi. So thank you for announcing me. When I usually talk to students about my topic of the PhD work, the first reaction is, well, ear recognition, do we really need that? That's exotic, isn't it? But when I had a look at the call for papers, and this is a short cutout of the image that is on the top of the conference website. Ear is actually listed along, well, let's say, biometrics worth to be listed, not under the point exotic. And when you have a closer look at the trait itself, you see that it's actually used very much in forensics. And when I was at vacation in Rome last week, I even noticed that in ancient Rome, people were conscious of the fact that the ear is actually a very individual trait. You have some statues here. I have taken photographs of the ear. Well, there are plenty of statues in Rome, so I can't guarantee that each of the ears is actually different. But it was a sign of a very good craftsmanship that not only the ear but the whole statue is very individual, and so Romans actually used it as a sign of good quality. So this work is not about ear recognition but about ear detection, and well, there's more than just 5 pieces of related work, but I would like to point out these 5 examples. The first one by Prakash and Gupta is probably best known among you because it was presented on the ICB last year, and it's also the work that is most compatible to the current one. There's also work by Joe et al., Ansari and Gupta, Chen and Banu. These are older works. You see the white numbers in the bars are the numbers of images that were used for getting the results. So yeah, the Joe et al., Ansari and Gupta, and Chen and Banu. Well, Ansari and Gupta is actually a 2D approach, but that was actually the approach that inspired us to get to the current one. Chen and Banu is probably the most well-known, and it's also closely related to our idea. But yeah, all those approaches were tested on a very small number of images. So what's actually solved based on not only the related work I just showed, but general in ear detection is detecting ears from profile images using either texture or the depth information. However, if we look at the databases that are currently available, we actually have pairs of images with 2D and 3D information. And the special thing about this is that it's co-registered. That means that for each point in the texture image, you find a corresponding depth information point in the 3D image. A second question is whether we could include additional structures in order to make the detection process more reliable, and whether we can find a method for describing the ear that is more robust against in-plane rotations. So for many classifier-based methods, for example, the method by Joe et al., it's not invariant to rotations at all. It's a sliding window approach, so you need normalized images before you start with the detection. So here's a short overview of our approach. We start with the depth image. So actually down here, we calculate the mean curvature and apply a threshold. With this threshold, we throw away all curvature information that is well, not curved enough on the surface, and we can do this because the ear has a very special curved surface. So what you see here is that in the ear region you have large connected regions after applying the threshold. We select those regions, we call them shapes now for the moment, and now do the fusion with the texture image, or actually the edge image. And because these images are co-registered, we already know that in the region where the ear is probably located, because we have large curvatures, we can find additional edges to have a more complete shape reconstruction. Based on all these components put together from 2D and 3D, we reconstruct ear candidates, apply a scoring system that will be described later on in this talk, and mark the best candidate, or actually the best groups of candidates, as the ear in the image. So one core idea of this is based on the fact that these images are in fact co-registered. So imagine you have one shape from the 3D image, it's the thick one here. Well, you don't know yet whether it's probably part of the ear or not, but if you can find other nicely curved connected edges near it, in a region that is simply dilated with a disc-shaped structuring element, you can consider these additional edges and try whether you could be able to reconstruct an ear with all of these components. After we have created such an ear candidate, we have to evaluate these candidates somehow, and this is done by this modular scoring scheme. We have 3 modules in total, that is the individual score, the relative score, and the context score. And each of these scores can be additionally enhanced with a weighting factor. And we need this because we don't really know in advance the pose of the person. So for full profile images, it's actually we can reconstruct pretty neat ears and evaluate them with just having the individual and the relative score. But the more we move off pose, which means away from the profile view, the more important becomes the context score. Moreover, it may be interesting to consider the image quality, because you can imagine that, for example, the curvature information will degrade if you have a low quality depth image. So the first component is actually answering the question, well, does that thing I've reconstructed from the shapes actually look like an ear? And how eerie is it? The second one compares, or is for comparing other related structures in the whole image, and decides, well, compared to the other shapes, is it still a good decision, or do I have better shapes in the image? And the third part, the context score, evaluates whether the position of the ear candidate is plausible for being an ear. The individual score is based on the context how of the reconstructed shape. We would expect a nice ear shape to be almost a half circle. We would expect it to be self-similar. That means if we have a large curvature up here, we expect a similar curvature down here, and we expect it to be open on one side. For the algorithm, it does not play a role which side is actually open, and it does not have to be a left or a right ear. At this point, the only thing we measure right now is whether this side here, this connection between points P1 and P2 exists. For the individual score, so we use the total slope from all the pixels. That means we add all the slopes locally, and we compute the ratio between A and B. We also compute how much, of the line is curled inside. And we also compute the ratio between the height of the total shape, so that means this and this. And well, for an ear we would expect it to be, let's say, 3 parts and 2 parts here. The relative score incorporates the fact that, well, how many, or if we have a set of initial shapes, how much did we have to adapt those shapes in order to reconstruct a proper ear outline, like shown here. The algorithm allows us to move the shapes a bit within a certain threshold, and also to interpolate a few pixels if they are missing. That can happen because the threshold does not account for these things. So it may happen that a few pixels are missing, the algorithm interpolates them again. Depending on how many pixels we have interpolated, however, we must assume that the initial position of the shape is probably not a suitable ear candidate, so we subtract from the relative score if we had to do much adaptations. Additionally, the relative score is able to exclude candidates in region with a low number of shapes. This is based on the assumption that in the actual ear region we would be able to reconstruct a large number of different ear candidates that cluster somewhere. I will show you one example of a typical error later on, and that will probably become more clear then. The third part, the context score, evaluates, well, let's assume the candidate I am looking at now is actually an ear. So I have found the whole outline of the ear. I have found the open point, and now we can compare the height of the outline with the distance from the orthogonal line to the edge of a silhouette. This is only done in the 3D image part, and the reason for this is that the silhouette, or finding the silhouette in the 3D image is very easy. We do not have to make additional edge detection steps or determining where the head is actually over, so we just measure the ending of the silhouette, so we have a large closed shape here, and this is very easy to detect. And yeah, we would expect the ratio between H and D inside an anatomically determined threshold. This can be adapted a little bit depending also on the pose, because D is not changing much but a little bit, so if you have frontal poses or if you approach frontal poses, D tends to get a little bit shorter. So if you run the algorithm for several times with different Ds, the impact is low, but the score actually accounts for both. For evaluating the approach, we used the following error metric. The detected region was compared with a manually marked ground truth. And we measure the total overlap in this formula, and we subtract the 2 types of error we can get. So we can have a region that was in the ground truth but not in the detected region of the image, and we can also have a region that was detected by the algorithm but it was not part of the ground truth. So for getting the total overlap, this will result in a value between 0 and 1. We would say that we would expect the algorithm to find at least 50% overlap between the manually annotated ground truth and the algorithm's belief where the ear actually is. For evaluation, we used 2 different databases. Both of them were collected by the University of Notre Dame. The first of them are left profile images only. So minus 90 degrees using the ISO definition of yaw poses, and we have only minor occlusions. Some subjects are wearing earrings. Sometimes the ear is a little bit covered by hair, but this is really minor occlusion. And we have a second one, the UND collection and YOF 2007. This one is much more challenging than J2. For our experiments, we used a subset of poses between 90 and 55 degrees, left and right. So this is a subject of about 3,500 images. The total database consists of about 7,000 images. Additional to the different yaw poses, we have occlusions through earrings and hair in the database, and for some images we do not have an ear at all, because it's fully covered by hair. In the first series of experiments, we used the UND-J2 database in order to determine whether the algorithm is rotation invariant. Well, as I mentioned, we only have left profile images, so if we flip the image horizontally, we can generate, well, right profile images, which are nicely comparable because we would expect exactly the same detection rate. In fact, we see slight differences of a few percentage, so we have 98.6 for the horizontally flipped, and detection rates of around 99% for the other pipelines. The reason why we observe this is because the reconstruction quality of the algorithm also depends on the order of the shapes they were added. So if you repeat the algorithm for several times and it selects different shapes, because this is randomized, the detection rate will slightly change because of the threshold we apply. So you remember we only accept images that have more than 50% overlap with the ground truth.
Okay. We have to go quicker now.
Oh, sorry. I'm in a few minutes. Okay, so I'll go quick, there is. And yeah, so the second pipeline is evaluating the impact on different poses. This is done on the off, so you see the performance decreases quite significantly when we approach the frontal poses. And also the impact of using the 2D data for the algorithm. And you see this is probably the most interesting aspect here, that for 3D data only, we get a detection rate of 93%, and if we use the fused algorithm, we get 99%. So let me just give me 2 more minutes to go over this quickly. So the pros, just one, okay. So the pros are that, well, we have a neat detection accuracy. It's invariant to rotation. We have some robustness to post variation, though that could be improved in the future. And the main advantage is probably that the algorithm gives us an initial approximation of the ear's outline, which is nice for normalization. And well, the cons is that, well, the runtime increases with the number of shapes. So if you have very detailed images with a large number of shapes, then the runtime will increase. It is possible to decrease the runtime again if you parallelize the algorithm. Our current implementation MATLAB takes about 5 seconds on average per image. And sometimes it may happen that the algorithm gets trapped by hair. Or as you see here, if no ear is visible at all, it can reconstruct a very nice ear from the nose outline. So to summarize, we found that the fusion of the co-registered texture and depth images overcomes the disadvantages of 3D analysis only. This is mainly because we cannot measure any curvatures at the edge of the silhouette, and if you have holes, then the complete curvature information gets lost, and we can reintroduce it using the texture image. We can actually come up with a very simple set of features to describe the ear shape, plus, as a third point, the context information from other face region increases the robustness against false positives in case an ear is visible. So in this case, no ear is visible. So the context information did not work very well, but in cases where the ear is visible, this works fine. So, thank you.
It is always important to have questions, so we can have just 2 quick questions, yeah? Do we have any questions? Oh, Sir.
How do you actually objectively assess the accuracy of your proposed scheme? How do you tell that this is accurate detection, this is not accurate detection?
This was just determined empirically. So we ran the algorithm the first time and we looked at the overlap between the manually annotated ground truth and the detected region, and we found that for the images it's sufficient to have a 50% overlap because the ground truth was marked by different people and some of the people were very nice in marking large ground truth regions. And the algorithm is more accurate, so it really detects the ear outline. So in these cases, you have the complete ear and a large region that is not in the detected region. There are additional statistics available, or I can make them available to you, where you can see that the ear is detected anyway, because you can evaluate the overlap or the 2 types of errors separately.
Okay, any other questions? I'll just ask a quick one, because I think it's important. On slide 3 you had a comparison, and it was, don't go to it, it was with other techniques. Were they all on the same database, or were they on different databases? Because all the numbers are quite different.
Well, they were, Prakash and Gupta was the same database. There was also HuNDJ2. The other ones were performing on, I think, previous versions of the database. So all of these are the HuND collections taken with the same capture device, but with less persons. So if you have a look on their website, there are several data sets available, and they used the previous ones.
Great, thank you.
Go to number 2. Yeah, very good. Okay, our next paper is on synthetic offline signature image generation, and is going to be presented by Miguel Ferreira Ballester from University de Las Palmas de Gran Canaria, Spain.
Thank you for your presentation. And this paper, it's about propose a method to generate synthetic signatures. And after a short introduction, it will be presented in 3 steps. The first one, we will define a signature model. The second one, we will define how the writer write. And finally, the ink model to obtain a real image. We'll finish with experiments and conclusions. About the signature, well, introduction. I think that the major problem all of us have is the database. It's a great problem, and the availability of large database and common verbiage is a problem that we spend a lot of time with it. The drawbacks or the problems of the database are that it is slow, costly, complex, and in the case of signature, it requires a high degree of cooperation of the donors. And of course, the legal issues about sharing databases. So an alternative is to synthesize biometrics samples. Obviously, we do not try to take away the real databases. The final test should be also with a real database. We are aware of that. And to generate synthetic traits is not new. In fact, there's plenty of them in the papers. We have found traits about fingerprint, face, iris, speech, and so on, even signature. The last 2 proposals we have found. The first one is proposed by Michael Guest that generates new samples of the same user using 2 online signatures of the user. The second one from Javier Galvalin generated new synthetic users using spectral analysis and the connected theory of human movements by Plamondon, I think it's over here. Then the above approaches synthesize online signatures offline, do not generate forgeries, and generate flourish-like signatures. Do not generate text inside the flourish. So in our work, we propose to generate offline signatures, static signatures, generating new identities, generating different genuine samples and even forgery samples. And we try to generate realistic images modeling the pen. The problem of text inside the flourish has not been addressed in this paper. The next one, perhaps. Well, oops. So, we will start with the signature model that involves the envelope and the signature path. We will follow the writer model, and we'll finish with the pen and ink, even a paper model. About the signature model, first we model the envelope. The envelope is generated with an active shape model, an ASM, and the ASM has been trained using the offline signature MCYT database. So just to have an example, the blue line, the blue dot line, is the average of the envelopes of the MCYT signature, and the red one has different envelopes for different users. Then inside the envelope, we define the strokes of the user. To do that, we have select randomly a random number of signature corners and join them with a line. We call to this trajectory the master signature path. Then, with that, we are going to generate the writer style of writing, how the writer writes. Then, the first variable or parameter of the writer is the inner variability, the difference between one sample and the next one. It is added drawing a ball around each corner and select a random dot inside each ball and join the new dots, new corners in a similar way that the master signature path. Then we have the signature path of each sample. Just to have a look about the different polygons we get. Upper, I think it doesn't work. There is the master signature path, and below, oops, you have different samples of the signature path. Then we have, once we have the variability of the writer model, we have to pass from the trajectory to this polygon to a handmade writing stroke. As the writing used to be modeled with a polynomial, usually the way we are doing that is to smoothing the trajectory with a polynomial cubic interpolation. Then the result is more or less as you can see in the light. Conventionally, we are doing that using a smoothing filter. I think it's known by all of you, called the Savitsky-Golay filter. It has two parameters, the filter. The first one is the key parameter, that is the polynomial degree, and the second one is the f parameter, that determines the smoothing value of the filter. Then changing the key value and the f value, you can change a little bit the way of the smoothing and to define also different writers. Just to have an example of the influence of the key and f value, you have for example there. Here is the lower key value, and here is the greatest in this case key value. You can see that you can change a little bit the writing style. Over this trajectory of the signature, we try to work out the speed of the pen on the trajectory. Why? Because we need to know, we relate the speed with the pressure. and the pressure gives us an approach of the ink in the stroke of the signature. So, to do that, we use the kinematic model proposed by Plamondon a few years ago. It is based on a delta log normal profile from the speed profile of the hand on the signature. The result, just applying the model, we have not improved it, it's just to copy. It's, for instance, for this case, we start here, and the first stroke, it starts to increase the speed, and decrease, then we are in this point, it increases again, it is the second maximum, this one is the third maximum, and finally we stop here with the speed equal to 0. It will be useful for us just to inverse that curve and have an approach of the pressure of the pen on the sheet. And the last parameter for the written model is to define the forgery variability. To do that in an easy way, we define, instead of a ball for the inner variability, we define a ring. Then the inner radius and the outer radius of the ring, we define the skill ability of a forgery to forge the user signature. So, if in this case, for instance, if we define the inner variability and the forger skillness, it's an easy case in this case to identify a forgery, and in this other case, where the ring is really narrow around the user variability, it will be a very difficult forger to detect. Obviously, for the forger to create forgery, we also change the key and the F value because the neuromuscular of the forger is different than the owner. So just to have an idea of the result, we have in this slide 3 different genuine samples, and here 3 different forgeries obtained with this model. When we have this figure, we pass to the pen model, just to obtain realistic images. As the method of writing use a ballpoint pen, we are going to model this tool. A ballpoint pen, or a ball pen, is based on a ball in the tip of the pen that rolling on the paper deposit ink over the paper. And the writing is produced in that way. From a reservoir, the ink coat the ball, and rolling the ball over the paper start to make the different spots, and we can see. Then we are modeling this effect to produce a realistic image. To do that, we define the spot with the ballpoint diameter, of course, and the shape of the spot, it's modeled with the inclination of the pen. If the pen is vertical, the spot is circular, and the spot is inclinated, the spot changes to ellipse. Then the spot in every pixel of the signature is different. To calculate the inclination, we suppose that the pen pivot on a point that is in the side of the paper and it's writing over here. By trigonometric relations, you work out the inclination, and from the inclination, we work out the shape of the ellipse. Once we have the shape, we have to define the ink profile, the gray profile of the spot. Usually, it is approached with a crop Gaussian, and Well, the height of the Gaussian is related with the speed. Greater speed, less higher. And the noise, and we add a little bit of noise to the Gaussian in order to emulate the position failures. Not the roller on the paper is not uniform. There are also a little bit of noise, and sometimes it fails to deposit the ink. Then, just to have an idea of the spots, we have simulated a thick line, and there are the spots we have produced. The last step, previous to apply it to the trajectory of the signature, is to model the ink. You know that the ball pen used to have 3 different kinds of inks: the fluid, viscose, and solid. It depends on the pen. Using the work of Catherine Frank, she defined the gray level histogram of each type of ink tape. Then we put a spot in every pixel of the stroke and equalize the histogram, trying to approach the histogram defined by Frank in her work. The effect is the next one. In the upper side, it's a real signature with a scan, and below we have a fully synthetic image. Then I think that the realistic of the image is really good. The paper model, it's okay. Then the experiments. Our target with experiments is to know the parameters of the synthetic database to adjust the performance results with a real database. Then the synthetic database parameters are, for the signature model, the number of corners inside the envelope. We have fixed that as a random number between 8 and 20. For the signature model, we have the radius of the ball for the genuine variability. It will be fixed, trying to approach the result of a real database. Then we have the forgery variability. We have 2 radius, the inner and outer radius of the ring. We will fix this radius, trying to approach a real database.
Miguel, could you move on to the results now?
Yeah.
We're running out of time.
We have also used 2 synthetic to database. One with just 1 pen model, and the last one using 18 models, 18 pen models. Then we have checked it with 2 databases. The first one is the MCYT, and the second one is the GPDS signature database, just to know the results. And we just to start to change the radius of the inner of the ball from 2.6 millimeters to 3.6 millimeters. And we realized that with 3 millimeters, the behavior of the synthetic database is really similar to the real ones. We did the same with the forgeries, and then we take 3 millimeters for the inner and 7 millimeters for the outer radio. This is an example of several genuine forgeries coming from the database, just the flourish. And the death curve, you can see that for the forgeries, the behavior is really similar for synthetic databases and for real databases. For genuine, you can see that the GPDS and the synthetic TV database are really similar, except in the case of the synthetic database with different pens. So we realize that this parameter, the verifier, is not robust to signature with different pens. And I think this database can help us to simulate different parameters that are not available in the usual database. So concluding, we have proposed a method for offline signature synthesis that include new signers, genuine samples, forged samples, and the ink model and the validation protocol. And now we are working on to add letters inside the flourish and adding new real features as aging and these kind of things. It was 6 months ago. By now, just to have a look, it is not in the paper. This is the new signature we are working out with them, adding the letters inside. Just to have a look. We will in the next paper, I hope. Oops. I'm finished.
Thank you. Thank you. Again, we've only got time for a couple of quick questions. So, Raymond.
Very interesting talk. Have you made some psychophysical tests with human beings to check if they feel that the signature were human-like? You can have a page and say, can you point out those who are synthetic and not?
Well, it's not easy, as you know. It depends on a lot of effects. Really, we follow, I think that Javier Garbali was in your lab, and talking with him, we try to emulate his work with you. Really, we do not add nothing new. Really, perhaps you want to collaborate, we will welcome, of course.
Thank you.
Okay, do we have another quick question? Oh, well, I'll ask it then. in other biometrics, people are always interested in aging, and we all know that as we get older, our signatures suddenly change with age. Have you considered putting aging in your process?
We are considering it, yes, of course. We are working with handwriting samples coming from ill people, mainly with Parkinson, that accelerate a little bit the aging effect on the handwriting. And we are, the model is prepared to consider that by now, but we have not worked yet on that.
No. Okay, thank you.
Lovely, thank you. Okay, our third talk is on form and trajectories and linguistic units, blah, blah, blah. And it's going to be presented by Javier Franco Pedroso, who's from the University Autónoma de Madrid. Okay. Thank you, Javier.
Thank you. So, I'm going to present this work entitled Form and Trajectories in Linguistic Unit for Test-Independent Speaker Recognition that has been done by my PhD advisor Joaquín González Rodríguez, Fernando Espinoza Cuadros, and myself. This is the outline of the presentation, so let's begin. This is the motivation of the work. As those of you familiar with the speaker verification field, state-of-the-art speaker recognition systems are based on spectral short-term features, but higher level features are very interesting for several reasons. First of all, they have also significant discriminative power, and so can be combined with the state-of-the-art short-term spectral system. But most important for us, they are more interpretable and acceptable in order to present in court, which makes them very suitable for forensic applications. So among these higher level features, we have selected form and frequencies for this work because they have a long tradition in forensic phonetics, and because recently some researchers, forensic researchers, have shown how to compute likelihood ratio from form and trajectories in linguistic units. But most of the studies have been done with manually or human supervised feature extraction, so the amount of data analyzed is always very limited. So the goals of the work are mainly to develop a fully automatic system capable to compute these likelihood ratios in linguistic units from these formal trajectories. And so we can test it on large standard factor databases like the NIST speaker recognition evaluation ones, and do an objective comparison with the state-of-the-art system based on MFCC features. And so we've done an analysis per linguistic unit, both in terms of discriminative power and calibration properties. And furthermore, we have analyzed the combinations between different linguistic units and between these linguistic units or this system based on formal trajectories and the state-of-the-art speaker recognition system based on MFCC features. So let's see the details of the system. This first step is the feature extraction process, which is for this formal trajectory extraction, we have used this open source tool called WaveSuffer in order to extract the first 3 formal frequencies with a 10 millisecond time resolution. And on the other hand, we have used an automatic speech recognition system in order to obtain a phone transcription of the speech recordings. And here we have an example of a diphone unit. These are the first 3 formal frequencies and the phonetic transcription. And then we code these trajectories by means of the DCT 5-order DCT for each of the formal trajectories, and then we concatenate these coefficients in just a single vector for each of the linguistic units analyzed. So finally we have, in this case for a diphone, we have a 15-dimension feature vector for this unit. And this is a whole speech recording where we can see the first 3 formal trajectories and the phonetic transcription. Here we can see also a word transcription of the recording. And here is the extracted feature vectors for the different units. So we can have words, diphone, triphones, or whatever. In this work, we have analyzed just phones and diphone units. And what we do with these features is to process via an independent system. So we have a number of likelihood ratio per trials equal to the number of units we have extracted. So these unit-dependent systems are based on Gaussian mixed model universal background model framework, and we train an independent model per unit. So we have 41 phone systems, 41 GMM UVM systems for phones and IDM for diphones. And every trial is processed by one of these, for every of these unit-dependent system. So for each trial we have a speaker model trained on the unit occurrences of the particular unit under analysis, and for the testing data we also extract these units and use it with the corresponding system. So, and then after obtaining a score per unit-dependent system, we made a calibration by means of logistic regression in a unit-dependent way. So we take all all the scores from one phone and calibrate independently from the other phones or iPhones or whatever. So finally we have 41 plus 98 likelihood ratio per trial. This is a diagram block of the system for a particular phone unit. So we have a background set of segments. We train a UVM for this unit by means of EM. And from the testing utterance, we extract the segment of that unit and make a maximum a posteriori adaptation. And we obtain the speaker model, and we do the same with the testing utterance, extracting these, the segments belonging to this unit and perform the scoring. So we obtain a score for this trial, for this A system, and the same will be done for another phone unit, and so on, until we have all the likelihood ratios per trial, which is equal to the number of units used. Furthermore, we have analyzed the combination of this unit-dependent system from this number of likelihood ratio per trials, and we have done two types of combination. First of all, we have fused the system belonging to the same type of unit, what we have called intra-unit fusions, and then we have fused from different unit types between them, what we have called inter-unit fusions. And we used two types of fusion techniques, the sum rule and the logistic regression. And in order to select the units to be fused, we also used two types of schemes. First, we take the best performing units and fuse together, the 5, 10, or whatever best performing units. And the other one was a sequential forward selection with the equal error rate as evaluation criterion. So we have a best performing unit as the set, initial set. We take the second best performing unit, we fuse. If the fusion improves the previous system, we keep this phone and continue. If the fusion doesn't improve, we don't use this unit. So let's see the experimental framework. We have used NIST speaker recognition evaluation. For those of you not familiar with this kind of evaluation, these are text-independent speaker verification competition organized by the US National Institute of Standards and Technology. And the data we have used belongs to the evaluations of 2004, 2005, and 2006 years. The speech recording consists of two sides of a telephonic conversation of about 5 minutes long and involves different headset and transmission channels. So there is a high variability in the database. And the evaluation protocol for the required task consists in you are given one conversation side of about 150 seconds for training a speaker model and another conversation side for testing. And there are thousands of trials involving hundreds of speakers. So this is the data partitioning we have used. For the background, we have used SRE-04 and 05. For development, we used the one-side tags from the SRE-04, 05, sorry. And for testing, we used the same task from SRE-06. And we have these MFCC-based reference systems in order to compare our approach that they used in contrast with the unit-dependent system that uses only the speeds belonging to the unit corresponding to that system. The system uses all the speeds available in a utterance. And we have this GMM UVM system and an I-vector system with this performance. This is not the best we can obtain with in speaker recognition with this technology, but it should be taken into account that we use no channel compensation, no score normalization, and we have just SRE 04 and 05 for background training. So let's see the results. In this table we have the 10 best performing phones ordered by equal error rate, increasing equal error rate. And here we have the phone unit, the equal error rate, and these two metrics are used to evaluate the calibration properties. I won't go into the details, just say that the difference between them is too small, so the calibration of each of the unit-dependent systems are quite well. And regarding the performance of the systems, we can see that each of the unit systems are far from the reference system, but it should be taken into account that in average, every of these systems uses about 5-6 seconds of speech, while the reference systems, the GMM, UVM, and the I-vector system based on MFCs uses all the 150 seconds available per utterance. And here we have the 10 best performing phones, the 10 best performing iPhones systems. The performance is worse because we have a limited amount of speech per trial, much less speech than the phone systems. So the performance is worse. But we have a lot of unit-dependent systems that can be combined. That is what we are going to see in next slides. Sorry. So here we can see the equal error rate of the fused system as a function of the number of fused phones. In this case, we are just fusing a phone system between them. And this, the line is for the M-best selection, and the dots are for the sequential forward selection. So we can see here that even though the individual performance of these systems are very far from the reference system, when fusing several units, we can go closer to the reference system. In this case, the reference system is just the GMM UVM. And for the best fusion, we can get about a 12% equal error rate fusing 18 units.
Do you have a quick?
Okay. This is the same for the diphone units, and we can obtain a 13% equal error rate fusing 41 units. So we need to fuse more diphones because their performance is worse, their individual performance. But we can get a performance close to the reference system. And this is fusing both phones and diphones system together. We can get about a 12% fusing 19 units. And finally, this is for the combination between these unit-dependent systems and state-of-the-art MFCC-based system. Here we have this brown bar represents the best fusion of the formal trajectories based system, which is about 12% equal error rate. That's the GMM UVM MFCC based system, and the fusion between them improves about 30% with respect to the GMM UVM system. And for I-vector system, we have a 17% relative improvement. So finally,
okay, we can leave those on the thing now. We're running out of time.
Okay.
Much, yeah. So leave them up there, yeah, while we answer some questions. Thank you. So again, we've got time for 2 very quick questions. Are we not going to get any questions? No? Why did you use DCT?
What?
Why did you use DCT? You could use PCA, which is a close approximation to DCT.
The thing is that people working with this kind of feature extraction are modeling the trajectories also with DCTs. So
This is all DCT?
Yeah.
Okay, cool. No questions? No, not from the speech people here? Oh, sir. Sir.
I just want to know how much is fast each of the single unit system that, for example, for one phone,
Yep.
unit, how fast is this compared to a state-of-the-art MFC Gen M-based system?
I don't have the values, but they process a smaller amount of speed, so it's quicker.
Okay, thank you.
Thank you.
Do you want this? Yeah. Okay. Oh, it still works.
Okay, our last talk is by the General Co-Chair. It's going to be presented by the General Co-Chair, and it's on biometric authentication with keystroke sign, presented by Aaron Ross.
Thank you, Mark. So this is the motivation for this research, and I'll give you the actual motivation in the next slide. So the stated motivation is in the context of active authentication, where the goal is to monitor an individual who is operating at a console, a terminal, and to continuously establish whether the individual at the terminal is the one who logged into the system at the start of the session. So the application domain that is being considered is continuous authentication. There is some element of forensics involved, as we will see later, and perhaps even the possibility of combining this with keystroke dynamics, again in line with the concept of continuous authentication. So just to offer some clarification between one-shot versus continuous authentication, you have a subject who is logging onto the system, and the subject leaves the system, and you have an imposter who can now enter into the system and start operating, although he is not the individual who logged onto the system in the first place. Now, that's a one-shot mechanism. In contrast, we have the continuous mechanism, continuous authentication mechanism. You have the subject logged on, and then the subject leaves the console, the terminal, and now when the imposter starts accessing the system, he or she is denied access because the system has been continually monitoring to ensure that the right individual is at the terminal. Now, there are several existing approaches based on face, for example, or even fingerprint, where you have a fingerprint sensor embedded in the mouse. Keystroke dynamics, which is very popular and has been reasonably researched in this domain, and also mouse movement, which has also been explored to ensure that the right individual is the one who's at the terminal. But once we start comparing these approaches along 3 dimensions, one being the authentication delay, how much time does it take before you can establish that the right individual is at the terminal? Well, for face and fingerprint, it can be immediate, whereas for keystroke and mouse, you need substantial amount of data before you can make that assessment. As far as privacy is concerned, and here we define privacy as the amount of information that is divulged beyond which is required. For mouse, perhaps it's very low, and for face and fingerprint, you have other concerns related to offering a primary biometric trait. But certainly for keystroke dynamics, because you have to log the keys that are being struck by the user, obviously you're offering more information than what is perhaps needed to make this assessment. Again, these are very qualitative assessments. We haven't done specific empirical analysis to make these statements. We're just doing this in a qualitative fashion. How about user cooperation? Well, in the case of keystroke and mouse, which are indicated on the left, lower left, you certainly do not have much user explicit cooperation required. But as you move to face and fingerprint, you would then require the user to interact in a certain way throughout the course of the session as the system tries to determine his or her identity through that session. So what about keystroke sound? So I said that, well, there are some motivations, and the real motivation is this. I walked into my lab one day and I heard a lot of keyboards being typed, and I asked myself, can I recognize who's typing the keyboard? And you know, do people have specific patterns? Of course, in terms of keystroke dynamics, the answer is yes, but in terms of the sound that the keyboard is offering. So something like this. I'm not sure if... All right, that was someone. It looks like sounds like a train, but and on a day when everyone is really working, those are multiple subjects typing. Obviously, because of the modulation of the system that we have here, the single channel, you're not hearing the exact sound. So keystroke sound, well, the pros and cons, it's expensive. You can use the built-in microphone, utilizes normal computer interaction. It avoids the direct logging of keystrokes, which is required by keystroke dynamics. And the negative aspect is, of course, that we need to filter the background noise. So now if we were to compare the approaches, again qualitatively, and you introduce the keystroke sounds as a potential cue here, this is how we think it would line up with respect to the 3 criteria that we stated earlier on. Now, is there any work in this domain? Yes, there is in the concept of forensics. One of the first works is by Asanov and Agrawal from IBM in 2004, where they tried to determine what keystroke was struck by the user based on the sound. Keyboard acoustic emanations in IEEE Symposium on Security and Privacy. That was the first work. Now, that work was further matured and strengthened by UCB, University of California, Berkeley, Zhuang et al., whose paper, by the way, was titled Keyboard Acoustic Emanations Revisited. And they were able to demonstrate that it's possible, based on the keyboard sound, to determine what characters were being struck on the keyboard. So that was the forensic aspect of their research. However, they did not enter into the territory of biometrics, trying to establish the identity within a session. So this is our setup. You have the monitor here. You have a Logitech cam, HD, webcam, which has both the video and the audio. And, you know, so you have a person typing. That's not me. And this is how we record the activity that is happening. So the proposed method, first and foremost, the keystroke sound is converted to a virtual alphabet, which is the crux of the technique. In order to do that, we segment the keystroke, the sound stream, and then extract MFCC features, which was even discussed in the previous presentation, from sound segments. So you're looking at the mel frequency, perceptual pitch. Then you do k-means clustering on the MFCC features. And when you do k-means clustering on these features, it's 256 dimensions, you get cluster centers. And these cluster centers are now referred to as virtual letter. And these virtual letters do not correspond to any letters in the keyboard, because we are doing the analysis in the sound domain. We are not trying to map this to any explicit letter in the keyboard. So in summary, the input acoustic stream is now converted to a string of virtual letters, and then digraph statistics, which is the relationship between two virtual letters, two adjacent consecutive virtual letters, is then used for encoding and matching purposes. So this is the basic approach that we have adopted. So there is training required, because the k-means clustering is the one that defines the virtual alphabet. So to compute the virtual alphabet and the frequency of occurrence, again, we must clarify that we're not trying to map the sound to any letter. It's just sound in itself, but the word letter is just used to denote that you have some kind of a string alphabet from which you're sampling. So you have the input sound stream, then the segmented sounds, and then you extract MFCC features from each segment, and then you put everything together and do k-means clustering. Output is a centroid or centroids, and each centroid is now the virtual letter. Now to do the extraction of features and matching, again you have the input sound stream. You segment it, which is very similar to what we had previously, and then MFCC features are extracted, and virtual letters are computed. Because we already have the cluster centroids, we can use the minimum distance criteria to now convert these segmented sounds into virtual letters. From these virtual letters, 3 types of features are extracted, highlighted in blue. You have the digraph latency, so we're not just looking at these letters individually, we're looking at them in pairs as diagrams, and so you have these digraph latency. That is the time it takes between those 2 distinct sounds. Digraph histogram, the frequency of observing 2 virtual letters consecutively, and also intra-letter statistics. Unlike the previous 2 features, which are digraphs, this particular feature is based on the virtual letter itself. More specifically, what are the MFCC features that are contributing to this specific thing? The algorithm layout is here and also in the notes, but very quickly, the temporal segmentation is based on looking at the power spectrum and taking high energy areas between 400 to 12,000 hertz. So this is how we do segmentation. It's a very basic method. Obviously will be confounded by background noise, something that we need to work on in the future, but this is what it gives us. And then how do we create the virtual letters? We extract 256 dimensional MFCC feature vectors from each key press. A key press has 3 parts: the finger striking the key striking the plate, and then the key being released from the plate. So there are 3 distinct sounds. Although 2 of these sounds occur so quickly and so closely that it's very difficult to distinguish between them. And again, each key press is about 40 milliseconds, which we have put as an empirical value in order to do the segmentation. Then we do the clustering process of the MFCC features to create the virtual alphabet. And so each key press sound is now mapped to a virtual letter. Now, if you were to look at the distribution of the virtual letters, we have projected this onto 2 dimensions. So what you see here are the first and the second principal components. The shape denotes the letter and the color the subject. But if we look at this more carefully, here you see clusters. The shape itself denotes the virtual letter, and the color denotes the subject. So you can see that the virtual letters are separated, and each subject might occur in multiple of these clusters. And this kind of gives us an understanding of the fact that a virtual letter may not correspond to the same keystroke letter for all subjects. In fact, for each subject, the same virtual letter might correspond to different keystroke letters. So these are some of the nuances of the technique. So for example, if this is the input sound, the virtual letters that we obtain here is 15231573, just as an example. Those would be the cluster centers corresponding to the first, fifth cluster, etc. And the latency between consecutive virtual letters can also be used as a feature. So here are the feature vectors summarized. The digraphs, which is the two virtual letters together, we use the top 50 digraphs. The image on the upper right is just to indicate the distribution of the frequencies of the virtual letters. There are 30 virtual letters that we extract, and then therefore this is a 30 by 30 matrix that you see there. The darker, the cooler the color, the less the frequency of observing it. The darker the color, the higher the frequency it is to observe it. Three sets of features. The first is the digraph statistic, which is the mean and standard deviation of latency within each digraph, the time between two virtual letters. The second one is the histogram, which is the relative frequency of different digraphs. Thirdly, intra-letter distance, which is the average of the MFCC features corresponding to each virtual letter. So again, these features were chosen ad hoc. There was no feature selection mechanism. These were the features that we decided to use in this work. And so just to provide the experimental results, the environment, same computer and keyboard, the typing data, first paragraph from a tale of two cities, the best of times, the worst of times, etc. 4 trials per subject in a single section. The hardware is a Logitech webcam, and 45 subjects for this initial research. Cross-validation, training done by 20 subjects, non-overlapping 25 subjects for testing. The gallery is the full paragraph of static text from the first trial, and the probe, 70% of paragraph of static text from the 4th trial. So there is a bit of overlap between the text that is used in the gallery and the text that is used in the probe, something that we are investigating further. There are 7 overlapping probes, and the gallery is in turn compared to these 7 overlapping probes. The experimental results indicate that this method needs more research, right? So equal error rate of 25% after fusing the 3 sets of features. But what are the interesting aspects of this? One, you need about 60 seconds worth of text typing before we can make a decision. And again, we were curious about how much of information we need before a decision could be made. But this seems to be a good starting point, as you'll see why. Because one thing is the encoding mechanism that we use is the MFCC, the MEL frequency, which is a perceptual pitch. And so we would like to observe if the true pitch can be used, perhaps in order to do the encoding. Secondly, the effect of using multiple keyboards, a more practical system. Static versus free text. Here, all subjects were using the same text. What happens if we have free text? We've already collected data for that. By the way, this particular database is available for further research, and there are directions in the paper on how that can be accessed. Fourthly, fusion with keystroke dynamics and comparative analysis with other biometric traits for continuous authentication. Now, I did mention, when I showed the equal error rate, which was, I'm sure, rather disappointing, but we've actually combined this with, thank you, Mark, to utilize the visual information of typing. And in fact, this is not in this paper, it's a forthcoming paper, where we did free text as opposed to static text, and we achieved a 99% true positive rate with 0.001 false positive rate with a 20-second probe. What did we do? We combined the acoustic sound coming from the keyboard with the visual of the person typing, the camera that was pointing toward the keyboard. And so using both, we were able to improve the performance further. So I'll stop there. We had fun doing this research because, sometimes one good thing we all enjoy is you wake up in the morning and you think of something and you can tell that to your students and tell them that there is a deadline for a conference. It's amazing how fast things can get done. But appreciate the time. Thank you very much.
Thank you. Okay, do we have any questions on this new biometrics? Sir?
Even if you're using the same text, is there any guarantee that if the user sits down differently, he won't produce totally different sounds?
Yeah, certainly. I think there are several covariates that impact. Specifically, as you rightly point out, the positioning of the keyboard with respect to the subject would be one aspect. And I'm assuming that's the aspect that you're referring to, in spite of having the static text. That's very true. Here, the keyboard was situated on a solid table, and if you were to take the keyboard and place it on your lap, certainly the dynamics of the situation would change. Again, like any biometric, we need a starting point, and then we go on to the harder problems.
Thank you. I think the keystroke sound recognition is very interesting, but I have a question. I think typing is a kind of habit, right? So I was wondering whether this kind of habit is easy to change or to be learned to attack our identification system.
Sure.
Thank you.
Thank you. So that's a good question. So, obviously it's a learned trait which changes over time. In fact, in our paper, we draw statistics about, how frequently or rather how long people have used this typing. But again, going back to the context of the work, this is for continuous authentication within a session. So for every session, the system is learning at the beginning on how the person types, and then throughout the course of that session, it is going to use the data that the thing that it created, the virtual alphabet, letters, digraphs that it created for that user throughout the course of the session. So once the user logs off and comes back in again, then the system would learn keep the typing patterns again. So that's the context: one-shot authentication versus continuous authentication over a single session. But as you rightly point out, if you were to leverage this across sessions, then that's a different problem, and it would certainly encounter the problems that you brought up.
Okay, we're only going to take one more question in that chap at the back corner.
So have you considered, in addition to authenticating or identifying users, to actually try to figure out, based on this audio information, which software is being used, and then use that as side information to improve the ROC curve?
Okay. We certainly haven't considered that, and I think you're perhaps also referring to the active authentication program that is funded by DARPA, which is doing something along the same lines. So I'm aware of some work in that domain, but that is something that we have not considered, and as you point out, there is a possibility of perhaps improving it, but I'm only speculating.
Okay, thank you, Arun.
Thank you.
And while we're there, let's just thank all the speakers in their session. They've done an excellent slides, yeah, but they do need to practice their timing a little more in the future.
Thanks.
Oh, yeah. Oh, sorry, just a sec. For the poster.